Hello, welcome back. We're going to continue our talk on sampling distributions. Specifically, this is section 7.2, part A. We're going to talk about sample proportions in 2 days here. All right, goal for today is to be able to describe a sampling distribution. Now, what is a sampling distribution? The sampling distribution of the sample proportion p hat describes the distribution of values taken by the sample proportion p hat in all possible samples of the same size from the same population. So again, that's the idea of a sampling distribution. We're not just looking at one sample, we're looking at all possible samples of the same size from that population. Okay, and then we're looking for the proportion that we get from that. Now it's a distribution, so we look at this and we can see what it looks like when it's plotted. Now, if you look here at the very top, we have 3 different proportions, okay, 10.1, 0.5, and 0.9. And you can kind of see where they're gathered. If the true proportion is 0.5, the sampling proportion is going to gather around that 0.5. So the sample proportion of all these samples would also center around that 0.5. Likewise with 0.10 and 0.9. But if you look at the lower proportion, this 0.5, this looks like it's more skewed to the right. If you look at the higher proportion, 0.9, this looks like it's skewed to the left. And the other thing I want to point out is this is only with 25 samples. Okay? We talked about this last time, but the bigger the sample size, the more it's going to center on the true mean. And this is the true mean proportion. So I upped this to 100. Now the sample size is 100, and you can see they all look fairly normal, approximately normal. So the bigger the sample size, the more normal it's going to look. Same proportions, just different sample size. Okay? Now, because we're kind of dealing with binomial distributions here, we looked at an example of that. We're sticking with the same proportion, the same sample size, like the number of trials. These are all staying the same, so it fits a binomial. So for a binomial, we want to look at sample proportions instead of just one single sample. Okay? So shape is going to be normal. We talked about that before. If n times p is greater than or equal to 10, and n times q is also greater than or equal to 10. That's something we've already learned. Now we've also learned that the center, the mean, is going to be n times p. Oops, n times p. But if we're trying to take a whole bunch of samples, we want to kind of average it out. So we're finding the average of all these proportions. We're going to divide it by however many we have. So we're going to divide it by n so that we have per 1, this will give us the actual true mean, which then when these cancel out, you get just p. Okay? And then our variability, we're going to take for binomial here, the standard deviation would be the square root of npq. We learned that. But again, we want it per 1, because we're going to take all these samples, divide it by however many there are, and get it per 1. That's the average standard deviation then. And we want to just simplify this. That would be your standard deviation. We're going to simplify this, though. The way you can put it all under 1 square root is if you square n. So if I go like this, npq, if I square the n and make it n squared, then I can put it under square root, because then the square root and the squared would cancel each other out if I wanted to get back to that. But I'm doing this so that I can cancel out an n, which would then reduce to just pq over n under that square root. And that ties into some of these important pieces of sampling distributions that I wanted to show to you. So choosing a simple random sample of size n from a population of n with a proportion of p successes. Let p hat be the sample proportion of successes. The shape. Again, the shape is going to be approximately normal as long as n times p and n times q are both greater than 10 or equal to 10. Excuse me. The center, the mean of the sampling distribution is going to be equal to the proportion. So the mean of the sampling distribution proportions is going to be the same as the true proportion from our population. Okay, if you average all those proportions from the samples, it's going to get you the true proportion. So average from samples, or from sampling distribution, this is the true proportion. And then likewise, variability, we just found that if the sampling distribution, as long as it's without replacement, we're assuming independence. That's important. And the n has to be less than or equal to 10% of the entire population. That's the other part that helps us with the independence. So independence condition. Assuming those things are true, the standard deviation would be square root of PQ over n. So make sure you have those down. We're going to now utilize those a little bit here with a couple examples. So here's the first one. Suppose that 71% of students at Hamilton High School regularly bring their charged Chromebook to class. Imagine taking a simple random sample of 100 students and calculating the proportion, the p-hat, the proportion of students in the sample who regularly bring their charged Chromebook to class. Let's say we did a sampling distribution and we found all possible 100 student samples. Identify the mean of all those p-hats. Well, you would assume that if you took all of those possible ones, it should, so the mean of all those p-hats should equal p, which should equal 0.71. So there's our mean of the sampling distribution, the mean of the proportions. Calculate and interpret the standard deviation of the sampling distribution of p-hat. So this is where we're going to utilize that other formula. So the standard deviation of p-hat would be the square root of p times q divided by n, which is 0.71 times 0.29 divided by, what did we say, 100? It's the square root of that. Okay? Ooh, backtrack. Can I even find this? What's the other thing we have to make sure we have? Come back to this. What's the other thing we have to make sure we have before we can actually find this standard deviation? Whoa. Not sure what happened there. We have to be able to tell if it's independent or not. So let's not forget to do that. I'll group that over here. So here's a friendly reminder. Step 1, independent. So is 100 less than 10% of all, what are we looking at here? Hamilton High School students, right? So we have about 1,600 students, so is 100 less than 0.1 times 1,600? Yes, it is. So we checked independence, we're good. Now, second, oh, I don't know why I did a 20. Second, find the standard deviation of these proportions. Okay, so now I'm back to here. If I do that math and I get the standard deviation, it is 0.0454. That's step 2. And step 3, interpret. It even asks you to interpret. So it's a good reminder to interpret. All right. Now, since this is a sampling distribution, we're looking for all possible. So if all possible samples of 100 Hamilton High School students were taken, the proportion of students with a charged Chromebook will typically vary by 0.0454 from the true proportion of 0.71. Okay? So that's kind of combining some ways that we've interpreted in the past. In this case, we're looking for all possible samples of 100 Hamilton High School students. So describe the shape of the sampling distribution, justify your answer. So we're going to assume that it's normal, but we have to check. Is n times p greater than or equal to 10? And is n times q, oops, greater than or equal to 10? Okay? If they are, we can assume normality. So 0.29, sorry, 0.71 is the one. 0.71 times 100 equals 71. That one's good. 0.29 times 100 is 29. That one's good. So we can assume that they will be approximately normal by the large counts condition. P hat we'll say, because we already said what that is, will be approximately normal. All right? So that kind of just talks about what we just were working on with these different things with the sampling distribution of proportions. All right? Now, one last example I want to get to is this one. Nope. This one. Nope. It is this one. Suppose that 70% of all dialysis patients, so that's something that you might have dealing with your kidneys, I believe, will survive for at least 5 years. A simple random sample of 90 new dialysis patients was taken. Calculate the mean and standard deviation of the sampling distribution for the proportion. Okay? So, we just did that. Number one, the mean. It's got to be 0.7. It's going to be the same as the true mean of the population. So now standard deviation, we have to check before we can do that, is 90 patients, less than 10% of all dialysis patients. So for this, we will assume it is. I assume that there's more than 900 dialysis patients everywhere. All right? Now, we can find the standard deviation of the p hat. That would be 0.7 times 0.3 divided by the n. We said of 90. Let's square root of that. I got 0.0483. All right, find the probability that fewer than 60% of those selected will survive for at least 5 years. So a little application with this. We found now a probability, we have a standard deviation. We know, well, we can check, is it normal? Well, let's check the n times p, so 90 times 0.7, 90 times 0.3. I believe it will be. So that's 63, and this is 27. Yes, yes, yes. Okay. So if we know it's normal, we can apply something here. can make a normal curve. We can make our mean 0.7, our standard deviation 0.0483. We already found those values. Now the question is, what's the probability that fewer than 60% will survive? So that's 0.6 over here, and it's fewer. This is nice because it works just the way our z-table will work. So take this 0.6 minus 0.7 divided by the standard deviation. Get our z-score, which happens to be a negative. Negative 2.07. And if I go to the left of that, it's very low on my z-score. It's 0.0192. So really, there's only a 1.92% chance of less than 60% surviving. So you see all the connections we can make here with what we've already learned. We have normal curves. If we know that they're normal, we can find mean and standard deviation. I know it's the mean proportion. It's the average proportion. So it is going to be a decimal. Same thing with the standard deviation. But this is what we're getting into with sample proportions. Okay? I'm going to challenge you to look at this scenario and see what you can do about it. Where it says 75% of U.S. adults get their news from social media. A random sample of 200 adults is drawn. I have some questions. I'm not going to go through them right now, but do you think you know what P and P hat are? Okay, could you define those? Could you describe the sampling distribution? Think SOC V. Okay. Looking at a sample of 200 adults and found 156, calculate the z-score. Find the probability that less than 156 of those selected from their news or get their news from social media. And then find the probability that between 70 and 80%. So it's all application with the same thing, and that is sampling distributions of proportions, also known as sample proportions. We'll get into more with the difference between sample proportions next time. That's all we're getting into today. That's section 7.2a. We'll see you next time.